Okay. And I'll be talking about Davis as I go through the talk. Hopefully you'll appreciate by the time I'm done that we're not just the sports teams that everybody wants to have as their homecoming opponent. But I'm going to take you basically through a little bit of the background, how we got where we are, and to an extent how you all and the food industry got where it is. And actually it's a story of spectacular success. The 20th century was defined scientifically and industrially by basically a single scientific field, chemistry. This was a spectacular success story. We learned about the world around us in molecular detail, and we brought that knowledge into, in essence, the world around us, and changed the human condition in unprecedented ways. And actually, you're sitting on, wearing, watching chemistry in action. So how did that work? At its core, chemistry is a reductionist science. The principle of chemistry, you take things apart in order to understand the individual elements and then put them back together. That's a wonderful model for science, and it turns out it's a wonderful model for industrializing that science. Because when you take things apart, isolate them, purify them, you can predict how they're going to behave. And so you do the same thing industrially. Now I know how material is going to behave. That's the basis of the spectacular success. And there are a lot of things that had changed, but perhaps one of the great successes was by taking food apart. So taking food apart into its component molecules, nutrition, as its early stages, could use what engineers call a fault model. A fault model is you take a complex system apart, you put it back together, you take one thing away. If that component was necessary, then the system basically fails. That principle was used for the molecules of food. And now we know, as mature scientific knowledge, every single molecule we need to grow, reproduce. Every vitamin, every mineral, every amino acid and fatty acid is actually known. Of the hundreds of thousands of possible molecules, we know every single one that you need. That's a spectacular scientific achievement by any criteria. Scientists are still debating how many planets there are in the solar system. We know everything you need to eat. That is a spectacular achievement. And you don't even appreciate how spectacular. That is to say, I would hazard a guess if I asked any of you how often you wake up in the morning and go to the silvered glass and check your neck to see how the goiter's doing. Most of you don't even know what a goiter is. But over 100 years ago, people of your age would genuinely be worried because you'd see them. You'd see people with these horrific, disfiguring swellings due to iodine deficiency. You'd see people with their legs bowed because of rickets. Not only have we understood and eliminated essential nutrient deficiency diseases as a disease, we've eliminated them from our mentality. We don't even think about them. You don't worry about them. That's the great success, a magnificent achievement. They're gone and you don't worry about them. What a wonderful scientific achievement. But how is it possible to bring that knowledge into practice? So when a society acquires knowledge, there's basically two ways you can deliver that to society. One, you put it into education, K to 12. We know how to do that. You put it into the curriculum, you teach kids, you test them. If they don't know it, they don't pass. We can educate the population well. Or you can industrialize it, put it into the world around them, and they get it even if they don't know it. And the decision for essential nutrients was to put it into the world around you. We don't teach people where they get iodine, we iodize salt. An absolutely brilliant public health strategy. Because in fact, you can get a nutrient deficiency disease at an age before which you can be educated. So the idea of nutrifying the food supply was a wonderful one. But we're not the same. Take Star Wars. I mean, does Liam Neeson and Natalie Portman have the same, in essence, nutrient requirements? Well, of course not. Why don't we personalize? Why don't we have to dose everyone in the exact amount they need? Because of a remarkable biological property. So if you don't get enough of an essential nutrient, you get a deficiency, everybody. But if you get enough, what happens if I take more than I need? Twice as much vitamin C, 5 times as much, 10 times as much, 100 times as much vitamin C as I need. What happens? I just pee and poo out the excess. It's a remarkable, in essence, biological process, and what it makes possible is a strategy for public health. How do I make sure everybody gets enough? I overdose everybody. Everybody gets more than they need, Liam gets all he needs, and Natalie Portman just pees out the excess. A wonderful strategy, and what that meant is you didn't need to individualize. We could make public recommendations for diet. We nutrified everything. Nutrition deficiency diseases gone. Magnificent achievement. But there were consequences. Because we, in essence, chose not to educate, diet and health became an elective. And we all know what happens when it's an elective. Students elect not to take it. And the food supply, free from the worry about essential nutrient deficiency diseases, you didn't worry about getting a goiter anymore, so the marketplace drove, in essence, the evolution of the food supply based on one dominating criterion: delicious. If you're going to compete in the marketplace today in food, you better be delicious. If you're not delicious, you can't compete. So the food supply has been getting more and more and more delicious because that's the key criteria on which we choose. Uh-oh. So we are an uneducated, ignorant population in this huge, hostile environment. What a surprise, we're not making good decisions. So that's basically the environment that this great success of chemistry has left us with. We should be the healthiest people in human history. We know more about health than ever. We invest more. Interestingly, in some criteria, we are spectacularly healthy. We will all live, you will all live a long life. The problem is the quality of that life isn't the same. In fact, some people are spectacularly healthy. Jerry and Roger are playing the sports they learned as children. They're both over 100. Spectacular success. On the other hand, the average person today is overweight, pre-diabetic, hypertensive, and genuinely compromised quality of life because of the diet they're consuming and its effect on them. So in fact, we are now seeing people living longer, but their health quality is deteriorating. And the epidemics of diseases are non-communicative, but they are debilitating. So the health is deteriorating for the population. Agriculture itself, its value proposition is in a state of chaos. There's no money in it. It's the lowest paid enterprise, even though it's the world's largest. There's enough money in it to even pay the workers a viable wage. And it's not sustainable. Perhaps the best example of this is milk. If I go through the San Francisco airport, go through security, they take away my beverage. So I go through security, what's the first thing I encounter? A kiosk to sell me back single-serving beverages. Not surprised. So in essence, the airport, single-serving water and single-serving milk are side by side. What's cheaper? The milk. What that means is to the consuming public, California dairy farmers are lowering the value of water by putting it through their cows. That's what agriculture has become, this massive cost-driven enterprise. Life sciences are still stuck in this reductionist, pharmaceutical-based, disease-centric model. Wait till you're sick, try and cure you. And science's great embarrassment, for 70 years, we have invested not in health, but in the diseases of middle-aged rich men. Full stop. That's the embarrassment. So, what we would like is to change that. We would like to be able to, in essence, recommend diets, lifestyles that literally prevent disease, improve your health. Great idea. Problem is we don't know how to do it. We have no idea, literally, how to intervene in healthy people to make them healthier. Because if I'm going to prevent disease, I literally have to make healthy people healthier in all aspects. If I get a diet that lowers the risk of one thing, but in so doing increases the risk of anything else, I haven't made you healthier at all. And we don't know what are the processes, the structures, the pathways on which we work so that they get better. We don't know how to do that. And there's three real problems with prevention. One, efficacy. What do I work on? What target do I act upon that makes healthy people healthier? Second, safety. It has to be completely safe. Again, if it makes a subset of the population less safe, it can't succeed. And finally, the value proposition. How much are you going to pay for a disease you're never going to get? How much did you pay for that iron today? Ironically, you pay more for salt that doesn't have iodine. So there are real problems going forward in prevention. So we don't know where we're going. We don't know how to get there. We need a new model. And that's, in essence, the framework that we began to research at the University of California, Davis. So we recognize there are new tools coming to food. So in fact, the science of the 21st century is biology. Biology is an integrative science. You look at the complexity of organisms, ecosystems. It recognizes the complexities of individuals. That's the new science. We're already industrializing it. If you ate yogurt today, you paid to consume a living organism. So the science is becoming, in essence, more relevant. Chemistry is changing. Chemistry is now looking at biology in accurate quantitative detail. The math is different. Or not. It's okay. So the new math is the math of big data. The data of large databases interrogated remotely. That is changing the world and already bringing to practice. If you use Google Maps to get here, then you're using big data. It's also coming into health. This is not an image. This is an NMR spectrum. It's an NMR spectrum acquired in a three-dimensionally oriented magnetic field. It's a data file. What that means is you can send that data file to anyone you want. That's my heart. It's a data file. I send it to a friend of mine, Matthias Friedrich. He's a cardiologist. And it turns out I have a small scar in the upper left where Susan Scott broke my heart in the 8th grade. But he's able with this data file remotely to tell me how my heart's doing. So math is completely changing. Don't quit math. Finally, engineering. Engineering is no longer the engineering of massive installations to crack petroleum, crack soybeans. It's small, personal, fast, furious devices. So those are the tool sets we're bringing to diet and health. So biology is all about genomes. The public has invested massively in sequencing organisms. The University of California, Davis is the largest repository of genomes in the world. Not just humans. We have viruses, bacteria, yeast, mold, algae, insects, plants, animals. We have a remarkable knowledge of the entire phylogenetic tree, and we can interrogate it genetically. And so we can ask a simple question. What evolved under the constant Darwinian selective pressure to be nourishing? Why don't we just ask evolution how to nourish, to be protective, preventative, and use the genomes to interrogate them to tell us, well, what should we eat? The problem is when you do that, you realize it's a war out there. If you look, what has been the strongest selective pressure throughout evolution? It's to avoid being eaten. And if you're still in the gene pool, you're good at it. So in fact, most of the organisms that we would want to eat, plants especially, they can't run away. They've developed remarkably clever strategies to avoid being eaten. Toxins, anti-nutritive factors. If you want to get rid of your major professor, plants will tell you. But nourishment, not so much. Turns out there's only one thing. Lactation. This remarkable process that came about very late in evolution and is the basis of spectacular success of mammals. And it's our model. It's the mother-infant pair. Mothers literally dissolve themselves to make milk. Everything costs them. If the component in milk doesn't help the infant, the pressure on the mother, the cost, drives it out of evolution. But if anything in the milk encourages the success of that infant relative to its genetic peers, it's hard to imagine anything under stronger positive selective pressure as a food component. And that Darwinian engine of nourishing healthy infants to be healthier has been going generation after generation for over 200 million years. And that's our model. So we've been taking lactation apart from marsupials to humans to figure out what is it that we should learn from this evolutionary history. So it's caused us to change our thinking about food in general. And let me give you an example. So remember the model, the mother-infant pair. The cost of the mother's massive. If it's not of value to the infant, it's going to be lost to evolution. Well, imagine our surprise taking human milk apart, and we find out that the third most abundant component in human milk is completely undigestible by babies. Why would mothers dissolve themselves to make something the baby can't even digest? So the first question is, what is it? Well, thank goodness we're at University of California, Davis. Carlito Labrilla, one of the leading analytical chemists in the world. He literally builds analytical instruments to take biopolymers apart and study them. He applies these methods to milk, and it turns out these are oligosaccharides, sugars in polymeric form, very stereospecific linkages between the sugars. And those linkages have no enzymes in the baby to break them apart, so the baby can't access the sugars. And it turns out there's not one of them, there's not two, there's dozens of them. Milk is full of this material. It's spectacular. So we know what it is. The big question, of course, is why would mothers do it? What does it do? So our thought, my thought, well, if it doesn't feed the baby, it must feed something else. It must feed bacteria. So we recruited to the program David Mills, professor at the University of California, Davis, world-famous microbiologist. He studies microbial communities from wine vats to human intestine. He developed a whole new way to, in essence, measure the growth of bacteria so he could test, do bacteria grow on human milk oligosaccharides? And he broke my heart. No. Bacteria can't break them down any more than a baby can. And he's trying bacteria after bacteria after bacteria, nothing. Oh, and then he finds one. What a surprise, from the intestine of breastfed infants. We sequence the entire genome of this bacterium. It's a bifidobacteria. It's a very select strain. In fact, it's quite different than most even bifidobacteria, 700 genes different. But when we mapped all of the oligosaccharide linkages for the sugars, in Bifidobacteria longum subspecies infantis, there were genes encoding enzymes to break down every single one of those linkages. This is clearly a bacteria co-evolved with the oligosaccharides in human milk. And that, of course, is the genius of milk. Mothers are recruiting another life form to babysit their baby. And they're making sure that this is the one that grows because this is the one that they feed. What a remarkably ingenious idea. So it's not just mothers and babies that are under this selective pressure, it's these bacteria. So we had an initial customer. Who would need this? Well, of course, breastfeed, breastfeed, breastfeed. But Mark Underwood, head of neonatology at the medical center at Davis, imagine his world. He takes babies from mothers, premature, typically born by cesarean section. That means they're born sterile. They get no bacteria from the mother. He puts them in an incubator, and those bacteria begin to acquire bacteria that will live with them the rest of their lives. And where are they coming from? The hospital. This is not the way you'd like to start life. So in fact, Mark, he said, could we try the strategy from that you've discovered? So we combine human milk and the oligosaccharides with Bifidobacteria infantis, and lo and behold, these premature babies filled up, and just like normal term babies, in essence, were protected by pathogens. So clearly this strategy works, and it needs to be brought to practice. So in fact, we decided that this needed to be, in essence, a product for the NICUs around the country, so we launched a company, the faculty involved, to do this. But while we were doing it, we began to realize if you want to understand a microbial community, you have to understand who's there, what are the bacteria there, what are they eating, and what are they making. And it turns out the way we've been taught about microbial communities is a little bit simplistic. In fact, it's rather beatific, right? You're portraying microbial communities as if they were gardens or lovely forests. Well, no. Those are photoautotrophic ecosystems. They get their energy from the light. You just have to reach up. That's not what it's like in your intestine. It's a war in there. It's dark, it's wet, it's anaerobic, and who lives, eats. And they eat each other. So it's much more appropriate to think of this as a carnivorous open zoo. So milk had to solve that problem. And the way it does it is by recruiting this very specific and protective bacterium and nourishing it all day, every day. So there's a flaw. Right? So mammals have developed this remarkable process of live birth. And one of the advantages of that is at the birth process, the bacteria from the mother transfer to the infant. In fact, now that we appreciate that, the whole birth process is starting to make sense. In fact, we rather comically watch children, they're watching a birth, and they say, "Oh, Dad, look, the mother's cleaning the baby." Well, yes, she's licking her baby all over, but technically she's not cleaning it. She's making sure that all of her bacteria transfer over. It turns out a very good idea. But modern medicine, inadvertently, antibiotics, cesarean sections, infant formula have been breaking that chain. In fact, this is not good news. We've been looking at cohorts now around the world, and it turns out where modern medicine has gone, with the best intentions, remember, antibiotics, miracle drugs, save more people and animals than anything else in history. C-sections, save mothers and babies. These are very necessary, valuable treatments, but they do have unintended consequences. And where we look, where modern medicine has been most successful, the percentage of babies that acquire the right bacteria is getting less and less. So we tried a clinical test. If you take babies in the greater Sacramento area, born either by C-section or normal birth, do they acquire bifidobacteria? We found none of them did. But if we give them the bifidobacteria as, in essence, a live product, within 48 hours, that bacteria grows and grows and multiplies. It grows spectacularly. It literally completely dominates the ecosystem community of that baby. In fact, it pushes all the other unpleasant bacteria out. Over 80% of the biomass of the diaper is a single strain of bacteria. And it's genuinely helping the baby get rid of all the bacteria that's acquired from the environment that are not particularly appropriate. And there's all sorts of things that this implies about the early education of the immune system of the baby, the acquisition of pathogens, the education of metabolism. But there's a rather interesting outcome. This is the poop coming out of a baby. So if a breastfed baby does not have the right bacteria, then the oligosaccharides keep streaming out. And in fact, pediatricians recommend mothers to anticipate from 4 to 9 loose diapers a day. However, if they get the bacteria literally within 48 hours, the oligosaccharides disappear, the bacteria numbers go up, and their metabolites, in essence, proliferate, acetate and lactate. They have 1 diaper a day. And the pH is interesting. The pH of, in essence, the top baby, pH 6. Basically, all pathogens can grow at pH 6. If the baby gets the right bacteria, in fact, the pH is 4.5. And those of you who know food microbiology, no pathogen grows at 4.5. This is a shelf-stable baby. So you're beginning to see that this is a really good idea. It's not new. We went back and looked at the literature from the 19th and early 20th century, before there was antibiotics and before there was C-sections, and there were some interesting papers. Tissier, the French microbiologist, the only tool he had in the 19th century for studying bacteria was the crude microscope. And that's what they did. And so the, in essence, nomenclature persists to this day. They looked at bacteria, they were round, they were rod-shaped, they were different sizes. That's how they described them. And of course, Tissier took this tool set to look at bacteria from all sorts of places, and not surprisingly, he looked at human poop. And lo and behold, oh my gosh, it's just full. Every imaginable size and shape. So it's clear that humans are full of bacteria. What's interesting, however, is at one point he looked at a breastfed baby, and he remarked, oh my gosh, there's only one there. And it's a pretty unusual shape, what he called a Y shape, which is bifid. So in fact, 100 years ago, and all the way back through human history, we had this, in essence, unusual ecosystem in breastfed babies. We've inadvertently knocked it out. So what have we learned? We're not alone. The bacteria in us are really important. There's more oligosaccharides in human milk than protein. Evolution has decided it's as important to feed the bacteria in the baby as the baby. We're going to have to change the way we look at health. A whole new way. We've got to feed the bacteria in us. They will become, in essence, our minions. It sounds like food is going to get unpleasant. We're going to have to eat bacteria and food for bacteria. Well, not so much. If you look at the valuable food products that have come through the culinary art, through history, chocolate, coffee, wine, cheese, beer, bread, kimchi, yogurt, they're not commodities. They're a combination of a commodity plus a microorganism. And as a result, those products are more stable, more nourishing, more valuable, and more delicious. So the future is actually going to be more nourishing, more safe, more stable, and more delicious. So it's up to you. If you're going to, in essence, have a better life, if you're going to make a better life for the world, you're going to have to be disruptive. There are tools available out there to start changing the way we grow, process, and deliver food. It's not going to be the way my generation made it. Sorry. But it's possible now to imagine a very different future for food and for the quality of lives. Thank you.